Hi, Jimmy. Hi, everyone. Thanks for having me. Can you give me a brief confirmation? Can you hear my voice?
We
Hi,
hear,
Paula.
yeah, we hear you well.
Great. And can you also see my screen?
It is just loading up on my end and we see your screen.
Perfect. Yeah, then let me start. First, something about myself. I'm Cecilia Curreli. I'm pursuing a PhD at the Technical University of Munich with Professor Daniel Kremers. And today I'm presenting the paper that we brought as CVPR, so a few weeks ago in Nashville, US, Nonisotropic Gaussian Diffusion for Realistic 3D Human Motion Prediction. Core code is on the left, code is on GitHub. If you want, you can give it a star. And we also have a demo on Hugging Face. And now let's see what it is about, starting with the task. What is human motion prediction? Is the task that from the past, like here, aims to predict the future. Now I want every one of you to take a guess by themselves. So what's going to happen next? The human is bending the knees. How is going to move next? Take your best guess. For example, it may go backwards and then put the ends up. This could be right. It's plausible, it's likely, but maybe you envision something like that. So we're turning towards the right and then going back. Or maybe you thought you were gonna crouch forward and put one leg up and so on. These are all possible, plausible futures, and these as well. So human motion prediction is the task that from the past aims to predict multiple futures, with the challenge being these futures have to be diverse and realistic at the same time. What does this mean more in detail? So let's take this motion here on the left. So white is our input and green is the ground truth from the data. We're putting our legs up and then down. And here we see the output of one baseline, rather old one. Yeah, my colleague and I call it the exorcist pose. This is not very realistic, isn't it? Here we have another one. So we're just sitting. This looks smoother, but it's also not highly realistic, right? And here you can see the output of our model, skeleton diffusion. Just we're losing our equilibrium and catching it back. And as you can see, it's diverse and realistic. Before I go more into that, let me give you an overview of like some other examples that our model can generate. So we have the same one of before. We have some different files with one. This is a bit slow motion, such that you can check it's really smooth. And what is this used for? So possible application are augmented reality or virtual reality, or very popular animation creation, video game content, everything that has to do with animation, where you from the past you want to generate possible realistic motions, and then going back more to the tangible world, autonomous driving, where you see the movement of pedestrians or kids and want to detect all possible edge cases and maybe plan and act accordingly. Or any possible application that has to do with human-robot interactions. So on the left, we have collaborative robots, for example, organizing, moving, planning to avoid collisions. And then we have assistive robots or elder care, where maybe you want to predict the possible motions of the patients and help them if they're going to fall down, or maybe support them in various tasks. Now more practical, I'm going to show you an application how you can use our model skeleton diffusion. So first, you have to look for a video. You just get a video depicting a human motion, and then you have to extract poses from this video and then forward them to our model skeleton diffusion. Our student, Jialing Yang, just prepared a demo, and we can see an example. So let's take this video. Oh, sorry. Well, okay, it's not playing, but this girl on the right is saying, oh, you're sitting all day up your desk, what would you like to do? It's a very typical video from YouTube or Instagram, TikTok, whatever. So this is how the first frame looked like. And sorry, I'm having some troubles. Yes, and from this video, you can extract a pose with another model. For example, this model from NeurIPS last year. And then with skeleton diffusion, you can generate different poses. You see on the right, the different futures. If you look at the one on the top left, we see it just rising from the chair, or on the top right, is standing up. My favorite one is the one on the bottom right, is just kicking the screen and yeah, doesn't want to sit anymore. Here we have another example. So from a running video, just by seeing half a second, the model can predict something with a bit more rhythm. It looks, yeah, quite realistic. Here we have another example. So it's from volleyball. And we can see that we're able to generate volleyball motion, realistic, particularly the last one. And this is another example from a movie showing that even if the previous pipeline fails and the input data are quite noisy, that our model can predict quite smooth futures, as you can see here. So if you know the part of the movie, then the person is sleeping afterwards. Yeah. Another example, the last one from Forrest Gump. Life is like a box of chocolates, if you know it. And yes, you can see lots of diversity. Yeah. Sorry again. So now, how do we achieve these results? Skeleton diffusion, the model we presented at CVPR, is a latent diffusion model that embeds an explicit inductive bias on the skeleton kinematic in both the architecture and the generative process. We do so in two different ways. Sorry, I'm really having a problem with my presentation. Let me check. Okay. I hope everything is fine now. So back to skeleton diffusion. You can see it's a latent diffusion model here in the middle. And it takes this input to the past, it encodes it into a latent space and then generate possible different futures. How can we achieve with this model realistic and diverse motion? So we have a twofold contribution. One is the graph attention architecture, which I will not go into detail today. And the other one is our novel Nonisotropic Gaussian Diffusion formulation, which is both a training and sampling formulation for, in case you've heard about it, the noise and diffusion generative models. This is actually what I want to talk about today, and I hope it's not too math intensive. Like I like math a lot. If you have any question, feel free to ask, and I will try my best to answer them later to make this process light enough. So probably some of you have heard the noise and diffusion model in the context of images. So you start with an image, like the one here on the left, and then you add a bit of noise, you obtain a noisy image, and you keep doing so until you reach pure white noise. And then during generation, you just take pure noise and denoises to obtain new realistic images. It's the latest generation procedure. And what we're interested here is this matrix. So this is the covariance matrix describing the noise that gets added between consecutive frames, which in the conventional and also original definition of the noise and diffusion model is isotropic. Isotropic meaning is a multiple of the identity matrix with all entries the same. And one step further, what does this mean for our task? So if you take a look at this matrix on the left, we have, we have we have, instead of pixels, every point in the matrix is indicating a joint position. Is indicating a joint position. So we have the hip and the knee and the spine and so on. As you can see, they're all uncorrelated. Yes, but if you take a look on the right, we know that these joints are connected, and that these connections are given by the adjacency matrix describing the skeleton graph. So this is actually given by the problem statement. As you can tell, it's not diagonal. And we believe that from this correlation, we can, from the connectivity, we can obtain correlations. So let's quickly go over through the math. We take this adjacency matrix given by the problem statement. We embed into another positive definitive matrix that can be substituted into the diffusion noising procedure, like here. And we see that this already performs much better. We obtain better performance and with various advantages that I will describe later. But we go one step further. So we see that during the generation process, we go from a coarse noise into more fine-grained image, or in our case, latent code of the human. And so we believe that the correlated noise plays a bigger role towards the end of the process. So we add the non-isotropic noise scheduler, resulting in this formulation, blending isotropic and non-isotropic noise. And this is our final formulation for Nonisotropic Gaussian diffusion. And we made it through the math. I hope I still have you here. Now we're going to go back to maybe something that everyone enjoys a bit more. So let's go talk about the architectures of skeleton diffusion. So I mentioned before, it's a latent diffusion model that's implemented as non-isotropic Gaussian diffusion for the task of human motion prediction. And since it's a latent diffusion models, the training stage is divided in two phases. So first, we're training the autoencoder, and then we're learning a suitable latent space that represents motions in a spatially temporally compressed manner. You can see it here. And then in this latent space, we learn non-isotropic diffusion. We learn with non-isotropic diffusion to generate new samples that then can be decoded into the motion you see on the right. About the first training stage, so this is how the autoencoder training looks like. So as you can see, we have a motion which is parameterized not as mesh, not as image, but we have 3D coordinates for every joint position and for every number of frames in our input video, usually half a second. And we are encoding this in a latent space that retains the notion of body joints and compress both the spatial dimensions of the 3D and the time into latent dimension. And then we just decode this latent codes conditioning on the past 2 frames. This is for consistency to avoid jumps between past and future. And in this way, we'll learn to reconstruct the input motion. And now that we've learned the latent space, we can train diffusion on top. So this is a conventional latent diffusion training besides the relaxation of the training objective. So let's go from the beginning. We take as input the past, we encode it into the latent space and give it as a conditioning to a denoising network that learns to generate multiple latent codes. And these codes are then decoded into different motions. So if during training we would just sample one code, for example, this one, and we would force this code to be similar to the code of the ground truth futures, this would considerably decrease the diversity of our final model. So we relaxed the training objective by sampling many different noise variables, they noise in them, and then we backpropagate the loss through the sample that is closest to the ground truth in this way. In practice, we just take 50 samples, as also some of the previous work did. Something interesting is, so we are training latent space diffusion with our non-isotropic Gaussian diffusion formulation. But as I mentioned before, the latent space has 2 dimensions, right? And we just can diffuse one dimension non-isotropically, the one that represents the joints. What should we do about the other dimension? We just decide to diffuse that one isotropically, meaning we assume uncorrelated information over there. And this results in lighter computation capabilities. And now let's take a look at the experiments. These are the results for a mass. We also compute experiments in other data sets. For example, as you can see here, human 3.6 million, which is quite famous. Freeman's is collected from RGB, while the previous 2 are collected with motion capture systems, so very precise data with sensors that are physically on the humans. Instead, Freeman or 3D poses in the wilds are collected from images, so they are noisy, but they can also contain, they actually contain realistic data, and so they're quite exciting. So you can check the experiments on the paper, but what I want to show you here on the table on the right is that in this table on the right is that we are able to show that previous method used to somehow cheat diversity. If you can see here, the diversity score is quite high. And previous work, and we of course also noticed, well, the output is not so realistic. I think we saw it before, right? It was the Exorcist one. But this diversity score is so high. Why? It's because these motions are not realistic, and we introduce some metrics to prove this. So the limbs are stretching or have some jitters, and yeah, we demonstrate this. This is interesting also beyond the domain of human motion prediction. In our ablation, we ablate our non-isotropic Gaussian diffusion against the isotropic counterpart. And we see that it outperforms the conventional isotropic one with a series of advantages. Not only higher performance, but this is achieved with fewer parameters, less iterations, and comes at no extra computational cost. The nice news is this: the non-isotropic Gaussian diffusion formulation is not restricted to humans or to human motions or human motion prediction. It can be applied to other domains by suitable choice of adjacency matrix, for example, and latent space. This is everything that I wanted to share with you today.